So this video's not finishing up. Continuing on with chapter 19, spectrophotometry, instruments, and applications, but shifting the focus from the instrument, which were what the first few videos were over, like the insides, how it works, and then we looked at how to calculate when we've got a mixture. And then now we're kind of focusing so let's look at when a molecule absorbs light. What the heck happens? And with this, we are going to kind of do some behind the scenes stuff. So I consider this the second half of the chapter, even though it's not evenly cut in half. So what happens when a molecule absorbs light? Part 1. Well, we have to review a little bit. Back in Gen Chem 1, you learned about atomic orbitals. So think electron configurations. 1s2, 2s2, 2p6, 3s2, that kind of stuff. Where you could take an element and write its electron configuration. We could do it for an ion. We could add or remove electrons and then write its electron configuration. So those are the atomic orbitals. S orbitals are spheres. P orbitals are like, people always call them the dumbbell. I think they look like the infinity symbol or like two balloons tied together. D orbitals look like four balloons tied together, except for the one weirdo that's like got a hula hoop around the middle, and so on and so on. Okay, so that's atomic orbitals. And that shows where electrons are distributed within the atom. Now, when we have a molecule, there are a couple different theories on what happens to orbitals when atoms become molecules. One of those theories is hybridization. So things like sp, sp2, sp3, sp3d, where the central atom hybridizes or mixes together their atomic orbitals and makes them into these new hybrids that are a mixture of S's and P's and sometimes D's to form the shapes, to get the bond angles, to make them look like the way they look. That's one theory. And that's the one that a lot of people use most of the time. In some ways, it's the easier theory of the two. The second one is molecular orbitals. And in molecular orbital theory, it's not just the central atom that is hybridizing its atomic orbitals to make new ones. It's every atom inside the entire molecule. So in other words, the molecular orbital theory is saying, well, in this picture here, I have a carbon, two hydrogens, and an oxygen making formaldehyde. Okay, so each of those atoms, the two hydrogens, the carbon, and the oxygen, would have mushed their orbitals together, their S and P and D orbitals that they had, to make these new atomic orbitals that are a mixture of all of those. And so these atomic orbitals, we see things like sigma and pi's and n's, and I'm going to talk about those in a little bit more detail, but we're going to be looking at things from the molecular orbital theory direction when we're looking at what happens with light. So you can have a molecular orbital electron configuration, just like you can have an atomic orbital electron configuration. We just see these sigmas and pi's instead of s's and p's. Okay, so what this is showing, well, I guess some more background. With molecular orbitals, there are bonding and anti-bonding. So bonding orbitals, and this is going to show up in a little bit, but I'm just going to go ahead and write it on this slide. It's positive overlap. So the electrons are overlapping, basically making bonds. Anti-bonding, which are, we see this asterisk. Let's see if I can write and talk at the same time. Anti-bonding are negative overlap, which means they're repelling. Okay, I can't write and talk. So they're working against a bond. They're repulsions. Okay, so electrons can be in either one of these situations. Things you have to remember is electrons form bonds, so that's positive overlap, that's sharing. But they're also negative charges, which are, negative, like charges repel, so negatives are going to repel from each other. So that's why we see both of these things happening. And you can kind of see in the pictures, all of these down here do not have the asterisk, so they're all bonding. But up here we have an asterisk, so it's an anti-bonding. And you see how there's a gap between them? They're not sharing, they're not overlapping. That's showing the repulsions. So that's just giving you kind of a visual of what's going on. Now, you didn't see these pictures that looked like this in Gen Chem 1. If you took it at St. Charles Community College, you might have seen something like this, where we had 3 columns and one is for one atom and one is for the other atom. We only looked at this for diatomic, which means 2 atoms. And then the center is the molecular orbitals. That's supposed to be a sigma. And then we did dots. What that maybe. Come on, pen. Can be my friend. There we go. There we go. So what this visual is trying to show, that this and this mushed together, this and, come on, pen. Okay. This and this mushed together to form the molecular orbitals that are here. So this is the molecular orbital. And then what happens is those electrons have to, these no longer exist because they mushed together to form this. So those electrons get moved into here. And then our molecular electron configuration would be sigma 1s2, sigma star 1s2. We've got 2 electrons in the bonding, 2 electrons in the anti-bonding. So we have equal amounts of attractions and repulsions, so we do not see a bond forming here. That's how you saw a visualization of molecular orbital theory. Again, that's not the same as this picture. This picture, we have 4 atoms instead of 2, so this is just what it looks like when it gets more complicated. And so you're not going to be expected to draw these to make something like this. We're going to be talking about what the electrons are doing inside of it. So, again, the whole point is what the heck happens when a molecule absorbs light. The molecular orbital theory is kind of our background. We need to know that because when a molecule absorbs a photon, a piece of light, okay, depending on the type of light, it gets promoted to an excited state. So the ground state is what the molecule looks like when it's at its lowest energy capabilities. Once it absorbs a photon, it goes to a higher energy. So it's an excited state. And depending on the type of photon, the amount of energy that's absorbed, we see its state, you know, it can increase in its rotations, it can increase in its vibrations, it can increase in where the electron is, like the electron physically moves. So these are just shown, so that's absorbing light, it gains energy, so the electrons in the molecule get excited and do something with that energy. If it wants to go back down to the ground state, it has to lose energy. It has to give that energy back out, and that's part of what we'll look at later in this chapter is what happens when it needs to, you know, get rid of that energy. So we'll be looking at that later. But what I wanted to show you with this picture here, back in Gen Chem 1 and also in things like organic, you're looking at hybridization and then also molecular shape and bond angles in general terms. So like this molecule would be trigonoplanar. It's got 3 electron domains, so its bond angles are all around 120 degrees. They're not all exactly 120 degrees because that double bond is repelling, but anyway, it's flat, kind of broken into 3 segments. That's at the ground state. When this molecule absorbs a photon and goes to the excited state, we can actually see that its shape changes, the bond angles change, the bond lengths change. So it actually truly changes in how it looks when it goes to the excited state. So we know that excited states and ground states are different and that we can tell if a molecule is in the excited or ground state as long as we've studied that molecule before. So that's why this is important. So again, just a reminder, orbitals in the molecular orbital theory that do not have those asterisks are bonding orbitals, so they are constructive. We're talking about attraction, we're talking about bonds, okay? Things that have asterisks are anti-bonding orbitals, so they're higher energy and they're repulsions between them. We will sometimes see, so sigma and pi are the symbols that we use here with molecular orbitals instead of S and P. This is kind of the molecular orbital version. But there are also N orbitals, which are the non-bonding orbitals. This is where the lone pair electrons are, the dots. That has nothing to do with bonding because they're just on one atom. And so we do have orbitals for that where those electrons are. And so in the molecular orbital theory, we'll see that, but just recognizing N means it's lone pair electrons, non-bonding electrons. Okay, so with an electronic transition, so when we have visible or ultraviolet light being shined at our molecule, that's enough light for an electron to physically move to the next highest level orbital. Okay, so that's what happens when visible or ultraviolet light is absorbed by a molecule. An electron in one molecular orbital moves up to a higher molecular orbital by taking the energy from the light, and it's enough energy to move it up to that higher energy level, that higher orbital. Okay, so formaldehyde, that was the molecule that I showed you the picture of, and I'm going to show it for you again here in a second. But when the lowest energy transition, so when formaldehyde absorbs light, the easiest electronic transition it has is to take an electron from the N to the pi star. So here's the molecular orbital diagram. Okay, so right now, this is where in the ground state, That's where the highest energy electrons are. So like this electron down here, it cannot move up. Sigma 1 cannot move to sigma 2 because sigma 2 is already full. Sigma 2 cannot move to sigma 3 because that's already full. Sigma 3 cannot move to sigma 4. So we see that we're going to be looking at the highest one because that's where it's got space to move up. So one of these electrons is going to have will gain that if it has enough energy to move up, it will move from N to pi star. So what those symbols are saying is we're just telling you the locations in the molecular orbital diagram where the electron's going to move. Okay, so it's going from a non-bonding, because I know N stands for non-bonding, to a pi, which pi bonds are involved with the double and triple bonds, but it's an anti-bonding pi orbital. Okay, so what would happen is down here in the N, we would only have one electron, and up here in the pi star, we would have one electron. Okay, so that would be an electronic transition. Now, when this electronic transition happens, there are two options on what it's going to look like. Those two options are the spin of the electron at the end of this. So back in Gen Chem 1, and I guess I drew the picture and just didn't explain, but when we have an orbital, we put one electron, oops, come on pen, okay, there we go. One electron pointing up and one electron pointing down. That has to do with there are all kinds of rules back with that, and we cannot have two electrons in an atom that had the exact same 4 quantum numbers, so their spin has to be different if they're in the same orbital. The pointing up one is +1/2, the pointing down one was -1/2. So anyway, in one orbital, we have to have an electron pointing up and an electron pointing down. Okay, so when this electron, remember there were 2 electrons in the N, right here, and one electron is going to get moved up to the pi star. So the two options, that's what this arrow is, option 1 and option 2. Okay, so option 1, in the N orbital and the pi star orbital, we see electrons with opposite spins, meaning one up, one down. Okay, it's kind of like it just moved from the N on up to the pi star. It didn't change how the electron was pointing. We have one pointing up and one pointing down. Okay, that's option 1. Now, option 2. So again, option 1. Come on, pen. Sorry, I know that was a super attractive noise that just happened. There we go. Not at all what I want to happen. Okay, option 1. There we go. So option 2, what happens? Well, both electrons end up pointing up. So same spin. And we wouldn't see them both pointing down. If you remember from when you first learned about this in Gen Chem 1, electrons typically go into an orbital pointing up first. The spin is maximized, like another one of those rules. So in this scenario, the electrons are going to both be pointing up, so they're the same spin. So the correct terminology for this, scenario 1, when they have opposite spins, this is called a singlet excited state. It's an excited state because we moved the electron from where its lowest energy was and we shoved it up there. But so that's why it's an excited state. It's a singlet. That's the terminology for when those electrons have opposite spins. One is pointing up and one is pointing down. Second scenario, when they both have pointing up spins, is called the triplet excited state. Again, it's an excited state because we promoted an electron to a higher energy level. And it's a triplet, that's the term for when both of them are pointing up. And so these symbols, S1, singlet state 1, T1, triplet state 1. Singlet state 0 is the ground state. That's like what it normally is. It's not possible for triplet state 0 to exist because that would be both of them pointing up in the same box. That's not allowed. Okay, so ground state is singlet state 0. It could go from S0 to S1, meaning when the electron is promoted, it's a singlet scenario, or it can go from S0 to T1. So when it's promoted, it goes to the triplet state. So the S and the T stand for singlet or triplet. You will need to know the difference between singlet and triplet. Okay, so here's the words. I put them down here. And the reason why it's the triplet state is called the triplet, even though there's not 3 electrons or anything. In a magnetic field, the triplet state, we see 3 different energy levels show up for the same scenario. And in the singlet state, we do not. So it's because of the way it interacts in a magnetic field. Okay, so something else to mention while we're here on this picture, and I'm going to go through it in the next slide, but while we're on this picture, I've got little number thingies right here. Okay, so those numbers are wavelengths. Those are the wavelengths of light that is necessary to make this excited state happen. So for the singlet state, 355 nanometers or lower wavelength, because the lower the wavelength, the higher energy, is necessary to make a singlet, and to make a triplet, 397 nanometers. So this is a higher energy. Apparently. So higher energy. Oh my gosh. How come it works fine normally, but not right now? There we go. I'm going to say higher. All right, E for energy, and lower E. So it's easier. Oh my gosh. Today is just super fun. It's still not there. Lower E. Okay. Lower E. There. So longer wavelengths means lower frequency. Lower frequency means lower energy. So it's easier to make a triplet. It takes less, not easier. It takes less energy for something to become a triplet state. It takes more energy for something to become a singlet state. And in my brain, the reason why that makes sense is we learned in Gen Chem 1 when we were doing electron configurations. If we have to have electrons in different orbitals, we do pointing up first. That is its default following the rules. So this is kind of following the rules from Gen Chem 1. Triplet state is when you move an electron up, both of them are pointing up. Okay, so that's the triplet state. It's easier. It takes less energy. Can I stop saying easier? It takes less energy to make a triplet than it does a singlet. So again, you need to know these words. You need to maybe be able to demonstrate this. Draw me a picture, kind of like this. You don't have to say n to pi star. This was just this specific example, but lower energy level to higher energy level. If you could draw it, then you know the differences between them. So this is just clarifying that. When it goes to the singlet state, it takes a wavelength of 355 nanometers. When it goes to the triplet state, it takes a wavelength of 397. And by the way, these numbers are specific to formaldehyde in this scenario. I just picked an example. But what we can take out of this in general, typically, triplet states take less energy than singlet states. So it takes less energy to, when an electron is excited, for it to become a triplet, and it takes more energy for it to become a singlet. That is a takeaway message from what we just talked about. So knowing the definitions for singlet and triplet, and then knowing that triplet states take less energy and singlet states take more energy to get to happen. And when this occurs, what happens is one of the non-bonding electrons moves to a different location. So it goes from the formaldehyde molecule is trigonal planar at the beginning, like when it's in its ground state. And then when that electron moves from the non-bonding to the pi star, what we did was we gave it another electron domain. So it went from having 3 electron domains to 4 electron domains. So it went into the tetrahedral electron domain geometry and ended up trigonal pyramid when we're looking at the 3 bonds. So trigonal pyramidal, oh my gosh. And so when that happened, the bonds are weaker because they get longer, and longer bonds are not as strong. Okay, so we're going to pause that one, and I'll pick up here in the next video.